Hi, geometry. Hold on. That's a little better. We are in Unit 7, Lesson 6. So, yep, today we're going to do Lesson 6. Just double check it. This first task statement, what do you notice, what do you wonder? I actually have a little video to show instead. Not that one. Not that one. This one. All right, so I don't think there is sound, so I think we'll be okay. So they're just pouring salt over a triangle that's sitting on top of a bottle. Okay, let's watch it again. All right, what do you notice? What do you wonder? All right, what do you see? Oh, wait. I'm not going to watch the whole thing, but I want to pause it. Okay, what do we see here? Let's get my pen out. Okay, what are those? Do you remember in the last lesson we made perpendicular bisectors that look something like this, and then we could draw a circle around that with this being the center. Okay, that's not what this one is. Okay, this one's different. So let's look. All right, that's what we see here. Now I can actually draw on it. Okay. I'm having some pen issues. I think we might be okay. All right, that's not the perpendicular bisector that we saw last time. Right? We did the perpendicular bisector. It would be about like this. And then we could draw a circle around it. Okay, with this being the radii. No, not with those being the radii, with this being the radii. These all being the exact same measurement. Is that what we drew here? I don't think so. I don't think these measurements are equal, okay, for that being the center of the circle. So nope, not the center. I think we can sort of make it up. And if I drew perpendicular bisectors, okay, these would be the radii of a circle, okay? That's a circle. That's not. All right? So yeah, I wonder what it is we've constructed here. I don't know. I wonder what it is. All right, so let's look at this images for launch. All right, for that launch thing, which was right here, the images for launch, let's see if we can do something else. So here, I have an angle, CAB, and I have circles. Okay, and the cool thing we know about circles is the distance from the center to the outside of the circle is a radius. And no matter the center to any outside of the circle, they're all going to be the same measurement. Okay, that's the definition of radius. So here, we are going to help visualize the distance from a point to the two sides of an angle, and we're going to develop the conjecture that an angle bisector is the set of points equidistant from the sides of an angle. Read that again. An angle bisector is the set of points equidistant from the sides of an angle. Okay, so let's look at this. So do you guys think it's possible to fit the circles between the rays, the two rays, so that the rays are tangent to the circle? Okay. moving it around. Grabbed it with my finger on my mouse pad. Okay? Okay, I'm trying to make a circle's tangent to the rays of that angle. And cool. All right, now I can't draw on this. I mean, I can, but it won't stay. That's my point of tangency, which means if I drew a line from there to the center, it's at a right angle. From here to the tangent, it's a right angle. And that right there is the center, right? Center, right angle where it's tangent, right angle where it's tangent, and that's the center. Okay, we've already learned that, right? Now, let's look at this. Oh, let's finish that. Okay, you see the centers? Watch this. Where the radius touches the circle, it's the same spot where the circle touches the angle. Now, I can actually, that ray goes through the center of every circle. So the distance from the center to the angle is the same distance from the center to the angle. Let's say it again in a different way. The distance from the center to this point of tangency is the same distance of this center to the point of tangency. And that tangent is where the circle hits the ray of angle CAB. So, okay, equal distance. Those are all equal distance. I should not mark them. Like this should be 1 tick, 1 tick, 2 ticks, 2 ticks, 3 ticks, 3 ticks, right? Because they're not equal to each other, they're equal to the circle that they're in. All right, so what I've constructed here is an angle bisector. You can read that, right? I'm trying to write fast because I know it's going to disappear. It's not writing fast. I tried. So what I constructed there was an angle bisector, okay? If I take out the circles, okay, that's an angle bisector. Ray, A, I could name it anything, is an angle bisector, okay? Let's see. Did I do everything I needed to do? Yep, I did. Cool. All right, so here, this is what we're talking about. Here is an angle BAC with two different sets of markings. I have BAC, BAC. Here, I've drawn a segment AE, and then from E to the ray, and from E to the ray are equal measurements, and they're at a right angle. Okay? So here I've drawn segment AH. I know that H to here is a right angle, H to there is a right angle. Cool. I don't know if they're equal or not. I've not put any tick marks here, right? But I do know that I bisected the angle. I bisected angle A. Here, I don't know that I bisected angle A, but I do know that these are congruent segments. Right? So point E is the same distance away from each of the two rays that form angle BAC. Make a conjecture about the angles EAB and EAC and prove it. Let's do that. I'm going to erase all this stuff. What do we know here? I know that those are congruent and these are congruent. I also know that this segment is congruent to itself, okay, because it's reflexive. AE is congruent to AE because it sees itself in a mirror. So I know that triangle, I need to name this X and Y. Triangle EXA is congruent to triangle EYA because of the hypotenuse leg triangle congruence theorem. Okay, it's the hypotenuse in one leg of a triangle is congruent to the hypotenuse in one leg of the other triangle. So therefore, those are congruent. Once I say the triangles are congruent, I can say that this angle is congruent to that angle because of, if I just name it 1 and 2, I can say angle 1 is congruent to angle 2 because of CPCTC. Congruent parts of congruent triangles are congruent. All right, so I just proved it. Angle EAB, which is angle 2, and angle EAC, which is angle 1, are congruent because of CPCTC. All right? Cool. Let's try the other side. Point H is on the angle bisector. Point H is on the angle bisector of angle BAC, right there. What can you prove about the distances from H to each ray? So we're trying to talk about this distance and that distance. All right. So I know that these two angles are congruent because they're both 90 degrees. I know these two angles are congruent because they're marked that way. I also know that side is congruent to itself. So HA is congruent to HA because they're reflexive. They're the same. So now I can say that triangle HAC is congruent to triangle HAB because of angle, side, triangle congruency theorem. Now, once I say that, I can say that those two segments are congruent. Let's just call it X and Y. HX is congruent to HY because of CPCTC. All right? So we proved it. We proved that those segments are congruent. They're of equal measure. Now, what if there are three sides? So two angle bisectors have been constructed in triangle ABC. They intersect at point G. So triangle ABC intersects at point G. BD is an angle bisector, and CE is an angle bisector. So sketch segments that show the distances from point G to each side of the triangle. Point G to each side of the triangle. I think that we're talking about the closest distance, like this. I'm touching this one at a right angle, I'm touching that one at a right angle. I didn't draw that right angle very well. And I'm sketching this one at a right angle because the shortest distance from G to the side of the triangle is a perpendicular line. Okay? All right, let's look. This is a much better drawing. Okay, so it's a drawing that I drew my red marker on in the last bit of video, but it's just better. So I'm drawing from here, perpendicular, perpendicular, perpendicular. Okay? All right, let me close this out. Actually, there is something else I want to show you. We have learned that, I hate that I can't draw on this so that it stays. Okay, oops, that I didn't want. Let's wait for it to disappear. Point G, if this is an angle bisector, point G is equidistant from here to here because it's an angle bisector. So this distance and this distance is equal because of how we've constructed. This is an angle bisector, so this distance is equal to this distance. Okay, we did that when we put all the circles into the applet, and we did that when we proved that in the second little example that this segment and this segment were equal, and we didn't have any of this stuff. Okay, we just had this angle with an angle bisector, and we proved that this segment and that segment were equal. Okay, so we can say that this segment and this segment is equal because of that angle bisector. Now I can also say that this angle bisector, that's supposed to be a circle. Wait for it. This segment and this segment are equal because that's an angle bisector. Okay, so think about it. Look at those, they're blue. And these were red because these are congruent to each other and these are congruent to each other. We can say these are congruent to each other. Okay, wait for it again. Because we can prove that these are congruent to each other and these are congruent to each other. Therefore, these are congruent to each other. Okay? Okay. Now let's close this out. Okay, we're back to our notes. So how do the distances from point G to sides AB and BC compare? They're equal. How do the distances from point G to sides AC and BC compare? They're equal. Will the third angle bisector pass through point G? So if I did this angle bisector, it is going to pass through point G. So we're saying that those are equal. Therefore, this segment and that segment are equal. Okay? Cool. Now that we know that, I could also insert a circle and center it. It's not easy to do. Center it again. If I were in GeoGebra, it'd be pretty sweet. Almost there. A little bit further. I think we're close enough. Okay? We were able to do it, which means that, nope. Oh, I did it wrong. Just a second. We're going to delete that. Oh, no. There we go. Let me see if I can point at this. Okay. I messed up again. Do you guys like it when I mess up? I always enjoyed it when my teacher messed up. It made me feel normal. It made me feel like I can learn this stuff. If my teacher is still making mistakes, then it's okay. I can learn it. There we go. All right, so I've got perpendicular with the radius and a tangent, perpendicular and perpendicular. Okay, inscribed circle. Last lesson we did circumscribed. This time we did inscribed. Okay, all right, let me check one thing. Yeah, let's do one more thing. See if I can delete that and this. All right, we've got some points here. So point F. Which side of the triangle is point F closest to? Okay, which side of the triangle is point F closest to? Well, it isn't. It's equidistant. Distant. I do not know what's going on here. To BC and AC because it's on the angle bisector. Okay, how about point E? Which side is it closest to? Okay, I'd say it's closest to BC, but it's equidistant to, let's see, AB and AC because it's on an angle bisector. Same reasoning as F. Point D, it's closest to AC because it's not on an angle bisector. All right. E is closest to BC, but equidistant from those two sides. F, it's equidistant from these sides, and I don't think it's closer to AB at all, but that's what we're going for. All right, so here I have a perpendicular bisector. That means any point on this line is equidistant. Okay, any point. And same here. This is an angle bisector. So any point on this line is equidistant to the rays of that angle. Perpendicular bisectors and angle bisectors. That's all.